We've just finished talking about ionic compounds which have ionic bonding present, and now we want to shift to the second type of bonding, and that is covalent bonding. Now this is an introduction to covalent bonding, and as soon as you are talking about covalent bonding, you're talking about a different category of substance compared to ionic compounds. You're talking about something we refer to as molecules. So as soon as you use the word molecule, you are indicating that the type of bonding that's present in that substance is covalent bonding as opposed to ionic bonding. Now molecules can be either molecular elements, abbreviating molecular. And an example of a molecular element are the diatomic elements that you were asked to memorize in Unit 1. And a quick reminder about those diatomic elements, I told you that they form an upside down L on the periodic table. So nitrogen, oxygen, and all of the halogens, fluorine, chlorine, bromine, iodine. And remember hydrogen, that exception is also, you find it on the left of the stair-step line, left of the periodic table, but it is a nonmetal and it is also a diatomic element. So you need to have those elements memorized. You can find molecules as either molecular elements, so example, hydrogen that we were talking about, or you can find molecules in the form of compounds, molecular compounds, which is a bigger and more commonly observed category. And water, for instance, a premier example of a molecular compound. It has to have more than one type of atom in order to be a compound. And if it is a molecular compound, the atoms would be nonmetal atoms only, and they would be held together by covalent bonding. So looking at covalent bonding, we are finding nonmetal atoms only. And we'll write that up above here, nonmetal atoms only involved in covalent bonding. This information that I'm discussing is found in the Chem 2A textbook, Chapter 6, Section 6, and in the Chem 22 textbook, Chapter 10, Section 4. So introducing with a definition of covalent bonding, and then looking at the simplest examples of it, which are molecular elements or the diatomic elements. That's what our goal is right now, to introduce what a covalent bond is and then to illustrate it in the simplest way possible, looking at diatomic elements, our molecular elements. So here's a definition of covalent bond. It's an electrostatic force of attraction. Right, so electrostatic, let's make that plural or that singular now. Electrostatic force of attraction operating between a shared electron pair and the nuclei of the two nonmetal atoms that are sharing the electron pair. Now I want to tell you that often when you look in the text, and maybe even in your textbook, I've taught out of so many now, that it doesn't really matter, but it's very common to see just this as a definition, what I put over here. Sharing of electrons between nonmetal atoms. And that's kind of a quick, user-friendly definition of covalent bond, but it does leave something out that I think is important as you're being introduced to bonding. All chemical bonds are electrostatic forces of attraction. And what does that mean? Same thing it meant in Unit 1, same thing it meant with ionic bonding. It means that opposite charge attracts. Negative charge wants to attract and stick to positive charge. So what's this electrostatic attraction occurring with a covalent bond? Well, the definition says that it occurs between a shared electron pair, there's our negative charge, and the two atoms who are sharing the electron pair, their nuclei, which are positively charged, attract and hold the shared electron pair. So hence the shortcut sharing of electrons, but it is an electrostatic force of attraction. It's actually easier to explain it by illustrating it. So let's jump in and take a look at the simplest diatomic element, hydrogen. So if we looked at the Lewis structure for hydrogen, it's in family 1A, although it doesn't really act like a metal at all. It's a non-metal, but it does have one valence electron. In fact, it only has one total electron. So the electron configuration for hydrogen, 1s1. Let me give myself a little more room here and write that a little lower, 1s1. And just to help illustrate, since we're introducing for the first time, I'm going to draw that s orbital spherical shape with that one electron. Now here is a second hydrogen atom, and of course it also has one valence electron, one total electron in that 1s1 orbital. So what's going to happen when these two hydrogen atoms get together? Can either one of them transfer an electron to the other? In other words, does one of their nuclei have the ability to pull the electron more closely to itself and just steal it, take it? Well, that can't be what's going on here. How do we know that? Because these are two identical atoms. They have the exact same number of protons in their nucleus. Neither one of these atoms can steal, quote, an electron from the other. It would be like you engaging in a tug of war with your identical clone. It ought to be a draw, a tie, if you were competing for electrons. So this cannot be a case of ionic bonding. We can't be observing ion formation because neither atom is capable of pulling the electron away from the other. So what do they do instead? Remember, hydrogen and helium both follow the duet rule. They do not want to get 8 electrons in their valence energy level because the first energy level can only hold 2 electrons in that s orbital, that 1s orbital. So what happens instead? These two atoms come close enough together to engage in what we call orbital overlap. So they come close enough together so that their 1s orbitals overlap and they share an electron pair between their two nuclei. And let's make this pop here a little more in black. They share an electron pair between their two nuclei. The nuclei have this positive charge, right? So that little spot there representing the nuclei. Nuclei are positively charged, the electrons are negatively charged, and the two electrons are experiencing the attraction of not just one proton, but 2 protons, one from each hydrogen atom. So the electrons are thrilled, so to speak. If they are sun worshippers, it's like they went outside and looked up in the sky and there's 2 suns that they feel the attraction to not just one, coming from the overlap of their 1s orbitals. 1s orbital overlap. And we call this attraction between one shared electron pair and two nuclei a covalent bond, a single covalent bond. And we represent that more simply and easily in this format. So if I draw a dash between two nonmetal atoms, I am trying to represent a single covalent bond. A sharing of one pair of electrons, one electron pair shared, equals a single covalent bond. And that's what you find holding two hydrogen atoms together in the diatomic hydrogen molecule. So what's going on when we take a look at the formation of oxygen, another diatomic element, from individual oxygen atoms? Well, if we take a look at the Lewis dot structure of oxygen, it's in family 6A. So I'm drawing those 6 valence electrons that are present in the oxygen atom. And here is our second oxygen atom. And let's draw it. So here are my 2 oxygen atoms, and I'm wanting to understand why it is stable for them to be found as a diatomic molecule instead of separate individual oxygen atoms. What's more favorable? What's lower in energy for them to come together and form a more stable diatomic molecule? Oxygen is following the octet rule, not the duet. Only hydrogen and helium follow the duet rule. All the other elements, we're looking at the octet rule to guide our understanding. So each oxygen atom has 6 valence electrons. These electrons are found in s and p orbitals in the second energy level. It gets too complicated to try to draw those orbitals, so we're going to leave that to your imagination here. We're just representing the total number of valence electrons. How can those orbitals come together so that each oxygen atom experiences an octet? Again, no electron transfer is going to be happening here. Neither oxygen nucleus can swipe the electrons from the other oxygen atom to try to gain 2 electrons to form an octet. They're identical atoms, identical nuclei. Like trying to engage in a tug of war with yourself, it should be a draw. So what's going to happen here? And just looking at this picture and imagining what we saw with the hydrogen molecule, even if we came together and shared 1 electron pair, each oxygen would then have only a total of 7 valence electrons, not 8. So remember, we can play around with these Lewis dot structures, these electron dot structures a little bit. And so I am going to move electrons and pair them up here and draw a picture like this. And why am I doing that? Because each oxygen has 6 valence electrons, would like to have a total of 8 valence electrons, so I can see that each oxygen is going to need to share 2 electrons in order to achieve a total of 8. It has 6. Each oxygen is going to need to share a total of 2 electrons in order to have an octet. So here we go. And we're going to show the formation now of a double covalent bond. And I haven't given myself quite enough room here, so let's space that a little bit further apart. So I'm showing 2 pairs of electrons being shared between the oxygen atoms. The remaining electrons that are not being shared are called lone electron pairs or unshared electron pairs. So in this picture, I see 2 pairs of electrons being shared between the oxygen, and then each oxygen has 2 unshared electron pairs or lone electron pairs. Now when I look at this drawing, I do this. And this is not trying to represent orbitals. This is trying to just count how many valence electrons I've accounted for. So in this circle around the oxygen, and since oxygen's symbol itself is a circle, maybe it will help if I make it pop a little in red. So looking at the circle I've drawn around the first oxygen atom, I can count that in this circle I have a total of 2, 4, 6, 8. 8 electrons. The first oxygen has an octet. And then looking at this second oxygen atom and drawing a circle around it, I see within the black circle I also have 2, 4, 6, 8 electrons around the second oxygen atom. So what we're schematically doing here is trying to represent orbital overlap These 2 oxygen atoms draw close enough together for orbital overlap to occur without trying to be cumbered by drawing the s orbitals, the p orbitals. The drawing would get very complex. So this is a schematic representing orbital overlap. But even this drawing is bulky and awkward to draw on a regular basis. So we simplify the drawing